Okay, so let's review what we learned last time. Last time we talked about the naming of the acid. An acid is the first you have a hydrogen and you have an anion with it. So that's an acid. So the acid involving two different kind. One is just the hydrogen plus the monoatomic ion, and also then we're going to add a hydrate in front of it and put the element's name and put ic acid. That's it. Hydrochloric acid, hydrofluoric acid, hydronitric acid. Okay, yeah. So with the monoatomic ion, we always add hydro in front. But if this guy combined with, if the hydrogen combined with a polyatomic ion, then that's different. Okay, we're not going to add hydro. Instead, you just need to look at what is the anion's name. If the anion ends with ATE, then you change the ATE to ic acid. If the anion is ITE, end with ITE, then you change the ITE to OUS. So generally, this is what we are doing for the acid. Okay, if it's polyatomic ion, just look at the name of the anion. Okay, if your ATE change to the ic acid, ITE change to the OUS acid. That's it. Okay, so this is how we name for the acid. For the naming for the molecular compounds, again, we need to specify how many number of each of the atoms of there, except the first atom. The first atom, if it is more than two, if it's more than one, we need to write the prefix. But if only just one atom for the first atom, then you don't have to. And we talk about the prefix you're gonna add is something like that: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Okay, so that's a prefix to specify how many number of the atom of there. And we also talking about for the molecular compound naming, when you have a compound, do not simplify the ratio, because those number of the atoms is what it exactly shows in the whole molecules. Okay, so do not simplify. The reason we simplify for the ionic compound is because ionic compound, the number of the elements over there is really based on the charge. Okay, we balance the formula based on the charge. It's not based on how many exactly the number of the atoms shows up there. Okay, it's just a ratio. Okay, those are just shows a ratio. So that's why you can simplify. But this one, the number shows in the molecules is exactly how many numbers in those molecules. Okay, so you cannot simplify. And those two molecules, you see, those two molecules are different. Those are two different molecules. So, and we talk about when you name the compounds, the first thing is you need to identify, is it an ionic compound or is it molecular compound? You need to identify what is that, because the rule of naming is different. So you need to identify those before you're doing the naming. And also we talk about the unit 2. First, we talk about what is the molar mass, right? What is the molar mass? The mole, what is the mole concept? Mole is just a number, a big number, 6.02 times 10 to the 23rd, a very big number. And we talk about, we also introduce the concept for molar mass, which means the mass of a molecule for a 1 mole of those substance. Okay, so the mass of 1 mole of the substance is called the molar mass. So generally, molar mass is still mass, but they have a number. They have a quantity, which is per 1 moles of those molecules, per 6.02 times 10 to the 23rd. Okay, and we also talk about how to figure out the molar mass of the certain compound. Okay, just need to figure out how many numbers of each of the elements in those compounds, and then you add the molar mass of those elements all together. That's it. For this case, for the hydrate, since this guy has some of the water attached, we're just seeing the dots of there in the middle is not a modification sign. It's just a talk about its attachment. So if you count the molar mass, it's not the molar mass of the copper sulfate time molar mass of the 5 of the water. It's addition. Okay, so the molar mass of the copper sulfate plus 5 moles of the water, the molar mass add together. Okay, this is how we count the molar mass. We also talk about the conversion between mass and mole. Okay, those two equations is what I hope you can remember. Okay, at the end of the semester, eventually, mass equal to mole multiply molar mass. And the mole equal to mass over molar mass. Okay, because we're converting mass to mole, mole to mass very, very frequently. Okay, so this is, I hope you're gonna use. And again, later, we're still going to use in those concepts. Okay, so that's why you're gonna remember this. It will help you to do the future questions very. Okay, we're going to use this in the unit 2. We're going to use it in the unit 3. We are also going to use it in the unit 4. Okay, so this is a very fundamental parts. Okay. All right. So here, this is the new study guide. This is new study guide. The first several page is give you the practice. For first page is talk about how to figure out the molar mass of the certain compound. Okay. Second page is try to figure out the mole to mass, mass to mole conversion. Okay. Yeah. And today we're going to talk about the content in the page 3. I'm going to assign some of the homework for you for today. Okay, so today we're going to have a homework. And the next Monday, next Tuesday, we're going to have a quiz. Okay, we're going to have a quiz, which is covered how to find the molar mass of certain compound. Okay, and based on the molar mass, how to figure out, and also the mass, how to figure out the moles. Okay, yeah, and something else, which is the topic we're going to cover for today. Okay. All right, so let's talk about the new content. Today we're going to talk about the conversion between mass to mole and to molecule numbers. Okay. Molecule numbers. Okay, so last time we already talked about this part, mass to mole. Okay, we know how to convert the mass to mole, but how can we convert the mole to molecule numbers? Well, so this is the conversion is 1 mole of the certain something is equal to 6.02 times 10 to the 23rd. This is by definition, right? We know the 1 mole is just this big number, just like 1 pair is equal to 2, 1 dozen is equal to 12. So 1 mole is just this big number, really big number. So if we have 1 mole of certain compounds, that means we just has a 6.02 times 10 to the 23rd of those compound, the molecules. Okay. So this is a molecule. But the point is, if you're talking about 1 mole of certain atoms, then the number could be also some atoms, right? So the unit of those number could change. That really depends on what kind of topic what kind of substance you're talking about. You're talking about atom, then that's just a number of atom. You talk about molecule, that's just a number of molecule. And if you're talking about ions, then that's just a number of the ions. That's it. So you see, 1 mole is that number. So how about 2 moles? If some substance has 2 moles, then that's just 2 of that much numbers. That makes sense? 3 moles is just triple that much numbers, right? And if it's a 1.5 moles, it's just 1.5 times these numbers. That makes sense, right? Yeah. So the mole could be a fraction. Don't have to be a whole number, because the mole is really big number, right? Even the fractions of mole still be a whole number of those single molecules. That makes sense, right? Okay. So to convert mole to molecule number, the molecule numbers actually is just equal to mole multiply 6.02 times 10 to the 23rd, right? This is a number of moles multiply 6.02 times 10 to the 23rd, and then we got the molecule numbers. Well, this equation, if you look at this equation, you can also figure out, okay, then if we have already have the molecule number and we try to figure out moles, how do we do? Based on this equation, we can also figure out, right? You just need to mole, then that's going to be just the molecule number divided by the 6.02 times 10 to the 23rd. That makes sense, right? So molecule number divided by this, then you can get a mole, right? You divide by 6.02 times 10 to the 23rd on both sides, then you got a mole. So mole will be just the molecule numbers divided by 6.02 times 10 to the 23rd. Okay, mole equal to molecule number divided by 6.02 times 10 to the 3rd. So this is another conversion between molecule numbers and moles. Okay, but usually when we do a question, it's not directly to convert a mole to molecule number. It's going to involve the mass part. Okay, it's going to involve the mass part. So let's just do one of the questions in your study guide, page in the page 4. In the page 4. In the page 4, question number 1. The page 4 question number 1 is talking about how many molecule numbers for 24 gram of the FeF3. Okay, FeF3. So we're going to convert this to the molecule numbers. The question is not say molecule numbers, but they talk about how many molecules. How many molecules is talk about how many molecule numbers. Okay. A lot of people make a mistake is they thought the molecule is talking about a mole. Okay, they thought that we're talking about how many molecules. They talk about how many moles. Okay, it's not. Mole is different from molecule number. Okay, so be careful when you read those questions. Molecule numbers. So we're looking for this. Well, then again, let's just write a map. This is a path how we do this. We know the mass can convert that to the mole. And we know mole can also convert that to the molecule numbers. So generally, this is a pathway. Some students may have no idea, where to get the mass to the molecule number. But once you write this down and you know the path. So obviously, we know the mass, and we're trying to figure out the molecule number. So first, you need to get the mass and to the molecules. From the mass to the mole. And then you convert the mole to the molecule number. So there's 2 steps you're going to work on, okay? To work on this, you can do step by step, which is 2 steps, right? you can first, well, let's just work on this. First step, you can convert mass to the mole. Okay, so mass, sorry. So mole of the F3, that should be equal to the mass of those divided by the molar mass of this. Okay, mass over mole mass, you got a mole. So the key is we probably need to figure out what is the molar mass of the ion Fe3. Okay, this is ion 3 fluoride. Then you just see, okay, this formula has 1 ion atoms and 3 fluoride atoms. Then you see that's gonna be ion 55.845. And plus 3 of the fluorides. So 3 times of the fluorides, 18.99984. Okay, so you add them together. You got 112.8402. And this is in gram per mole. Okay, so now you got the mass. Mass is 24 gram and divided by the molar mass 112.8402, and this is in gram per mole. You see, every time when I do the calculation, I'm putting the units with it because those numbers has a meaning. You see, the gram and gram canceled, then the moles flip over, then we got a mole. 24 divided by 112.8402, and you got 0.2127. And this is in mole. Okay, so since this number is not a final number, it's an intermediate number, so we're going to keep as long as possible. And then second step is we're going to convert mole to the molecules. Okay, convert mole to the molecules. Well, then it's just a 0.2127, and we know the molecule number should be equal to mole multiply 6.02 times 10 to the 23rd, right? So this is the what we got. You got a mole 0.2127, and you time 6.02 times 10 to the 23rd. Okay, and then you will got the molecule numbers. Okay, so we got 1.28 times 10 to the 23rd. And this is number of the molecules. We have 24 gram has that much of number of the molecules. Okay, yeah, that makes sense. Okay, but the point is, I think that the key has a little bit different. I didn't change that. This one only 2 sig fig. So the answer, you're gonna keep 2 sig fig, right? So the answer is not 1.28. Instead, it's 1.3 times 10 to the 23rd. Okay, so this is how we count. All right. Yeah. So again, this is how we convert molecule to convert the gram to molecules. Well, if you want to do, if you don't want to do this step by step, you can also combine together as a whole equation. Usually this is, if you do that more frequently, you can do this. This is what I do normally, okay? So what do? We just set up a long equation, okay? So first, let's see what we have. We have a 24 gram, okay? So generally, we just combine those two together. We didn't do anything else. We just combine those two together. So first, we have a 24 gram of those ions and the molecules. And then first, what we do, we just time two conversion. So first, we convert the mass to the moles. Okay, the mole, how do we represent a mole? So we'll try to cancel the mass and we got a moles, right? So we cancel the mass of the ion. We got a mole of the ion, the FeF3, okay? So based on the molar mass is 1 mole of the molar mass equal to 112.8402 gram. Okay, because this is by definition is molar mass. Molar mass unit is gram per 1 mole, right? So if we set up the equation, it's just 1 mole of this equal to that much gram. So in this case, the gram of that and the gram of that is canceled. Okay, then we got how many moles? But your setup is still same, 24 divided by this number, right? Just like this. Okay, but just a little bit different. This is time the conversion factors. So once we got moles of the stuff, then again, what we do? We just need to time 1 mole of this. 1 mole is equal to 6.02 times 10 to the 23rd. So you see the 1 mole and a mole of this is canceled. Now we just multiply this number, which is the second step. Okay, so generally you combine those two steps together, and then you're still doing the same equations, still doing the same calculation. You see the unit is canceled. Every unit is canceled. There's gonna be no unit over here. And then this is number. You can write this is number of the molecules. And then since we cancel all the units, then you will recognize the final calculation is just 24 multiplied by 1 by 6.02 times 10 to the 23rd and divided by 112.8402 times 1. And when you do the calculation, generally it's the same thing. All right, yeah. So this is generally how we do if we try to combine things together. Okay. If you do things more frequently, then you will think this way is more easy to work. Okay, it's more faster, much more faster. All right. Any questions? No. Okay, then let's talk about another questions. So in the future, I'm going to just combine those all together. So let's look at another question. So if we have a molecule numbers, and then how can we convert to the gram? So question number 7. This we have 9.4 times 10 to the 25th of the molecules. And then molecule of the hydrogen. So how to get the gram of the hydrogen? Okay, so it's the same thing. And since we have the molecule, right, based on the map that we shows above, you have a molecule numbers. So you have to convert that to the moles and then convert the moles back to the mass. Okay, so mole, you see, mole is a very important concept. They connect quite a lot of things. Okay, yeah, mole can convert to mass, mole can convert to the molecules. So everything, if you want to convert from mass to molecule or molecule to mass, you have to convert to the mole first. So we're going to convert the molecule, and then you figure out how many moles and how many moles to how many grams of the molecule. Okay, so let's say first we're going to set up the equation. What we have a 9.4 times 10 to the 25th of this. And we know this number have to divide by the Avogadro's number, right? To figure out how many moles. That's because 1 mole of this molecule equal to 6.02 times 10 to the 23rd of these molecules. Okay, 1 mole of this equal to that much of molecules. So you divide by that. And then you will figure out how many moles. By this division, then you will got how many moles. And then from mole to the mass, mole time molar mass, you got a mass. Okay, which means we just need to multiply a molar mass of the hydrogen. Okay, hydrogen is 1.008 gram per mole, you time 2. Then you got a molar mass of hydrogen, which is 2.016 gram per mole, which is the hydrogen molecule. And by the way, hydrogen always shows as a diatomic molecule, which means they have 2 of the molecules aggregate together to make 1 hydrogen elements. Okay, this is always happens. So naturally, you will see just H2 instead of CH. Okay, yeah. So you multiply the molar mass, which is 2.016 gram of the hydrogen per 1 mole of the hydrogens. So if you see those are canceled out, and the leftover will be just the mass of the hydrogen. This one again, emphasize again. When you do this, you have to put the parentheses in the bottom parts, okay? Otherwise, a lot of questions, a lot of cases, when you type those into the calculator, you may got it wrong if you do not put the parentheses, okay? So let's just work on this. 9.4 times 10 to the 25th times 1 times 2.016 divided by parentheses 6.02 times 10 to the 23rd. And here, that's going to be the answer. 314, okay, 314.8. 314.8. And this unit is in gram because here you see the leftover unit is in gram. So this is in gram over here. This is how many gram of the hydrogen shows over here. Well, if you look at the questions, the question only give us 2 sig fig. So the answer, you're going to only keep 2 sig fig. To keep 2 sig fig, the answer will be 310 gram, okay? Or you can write like a 3.1 times 10 to the 10th, and 10 to the 1 first. You can also do things like, 10 to the seconds, gram per hydrogen. This is also fine. Okay, yeah. So, any questions? No question? Okay, so let's take a break and we will talk about something new. Okay, yeah. I'm going to assign some of the homework for those. Okay,
Yeah, I mean, I was just using it. But yeah, I have. Yes. classes. Walking down the hall and it's like, oh. That's just. Brother, what are you doing? I'm getting the same thing out of. Oh, this is.
Okay, so the next part, we're going to talk about the percent composition. Actually, we already talked about percent composition in the lab last time. Okay, so percent composition. Let me just clean this. So percent composition, generally, what does that mean for percent composition? We already did that in our last lab 20, first part, okay? For example, we talk about percent composition for copper to oxide. It just shows, okay, if we talk about what is the percent composition for copper to oxide, the meaning is just please to figure out what is the copper percentage by mass and what is the oxygen percentage by mass. That's it. Okay, so that is just the percent composition's meaning. Okay, so last time we already talked about how to figure out the mass percent for the percent composition for copper percent and oxygen. Well, the copper percentage, that's going to be the copper of the mass of the copper, right? And divided by the mass of the total copper to oxide. And then your time 100. This is how you figure out the percentage. That makes sense, right? Yeah. This is, and also this is what we talk about. And but in last time in the lab, we talk about the percent composition. You have two different ways to do. One way is based on your experiments, you figure out the percentage. Or you can, based on the molar mass, you can also figure out the theoretical copper percent, right? This is what we talked about last time. So generally, the oxygen is doing the same thing. You can, using the oxygen, the mass, and over the copper oxide, the mass, you can do this. Or we talked about last time, you can also using the molar mass. Okay, yeah, mass, molar mass, they both can do the same work. Okay, but the point is, if you're using mass, obviously this is coming from your experiment. Okay, then you got experimental data. Using the molar mass, then that's coming from your theoretical data. You got a theoretical data, right? This is what we talk about. Okay, so now let's just do one more practice. Okay, so please to figure out what is the sodium carbonate percent composition. Well, generally is the same thing. Then that means we need to figure out, this is try to figure out the theoretical data. Okay, sodium percent, carbon percent, and oxygen percent. All right, so here, well, if you're talking about theoretical, that means we're going to using molar mass to figure out. It's doing the same thing, which means you should using the molar mass of the sodium. But the point is, not just the molar mass of sodium. You need to count the overall mass of sodium in the whole compound. Since this guy has 2 of the sodium, so you need to have the molar mass of sodium times 2. That makes sense, right? Yeah, because you need to count all the sodiums over there, okay? And then you divide by the molar mass of the sodium to sodium carbonate, okay? Yeah, You knock your head because you know it, okay? Not just I want to see, okay? Then you time 100. So the molar mass of sodium is 22.9898. And you time 2. This is a gram per mole. And the total one, we can just measure the total one because we're going to use quite often. So 22.9898. You time 2 plus carbon. Carbon is 12.0108. And plus, since we have only one carbon, plus 3 of the oxygen, which is 15.9994 and time 3. So this is the molar mass of the sodium carbonate. Okay, so 105.9886. And this is in gram per mole. Okay, 1 mole of the sodium carbonate is that much gram. Okay, so you divide by the molar mass of the whole compound. And then you time 100. Then you got the percentage, okay? So, or you just write 100%. So let's see. So 22.9898 and time 2, okay? We have 2 of sodium and divided by 105.9886. And your time 100, you got a 43.4, okay, 43.4. So 43.4, that's percent, okay? So the mass percent or percent composition for sodium percent is 43.4%, okay? And for the carbon, it's doing the same thing. We're going to use the molar mass of the carbon divided by molar mass of the sodium carbonate. And your time 100. Since this guy only just has 1 carbon in the formula, so just write 1 carbon. 12.0108 is gram per mole divided by 105.9886 gram per mole. And you will see it's a gram per mole all canceled. So the percent, there's no unit for the percent. Okay. You time 100%. And you see 12.0108 divided by 105.9886 time 100, 11.3. 11.3%. Okay. So last one, oxygen. Again, that's going to be molar mass of the oxygen. Since this guy have a 3 of oxygen over here, so you need to count 3 times 3 over here and divide by the molar mass of the sodium carbonate. And your time 100 over here. So that's a 15.9994, you times 3 divided by 105.9886 and you time 100%. Okay, 15.9994 times 3 divided by 105.9886. Okay. And your time 100. 45.3. 45.3%. So those percentage numbers, that's gonna be the percent composition for each of the elements. Make sense, right? Okay. All right, so the next part I'm going to ask, what do you think? those three numbers. What's the relationship between those three numbers? So if we add those three numbers, what's the number we can get? Should be 100. Okay, should be 100%, because this is where the come from. The percentage, add them together, should be 100%, right? Should be 100%. Okay, so those are add together should give us 100%. Otherwise, that means your calculation got wrong. Okay, yeah. So that is why, if we know there's an unknown, for example, if we have a compound combined with oxygen and some of certain metals, okay, certain metals, some of the metals plus oxygen, and we got the oxygen percent in this compound is 42.1%. That means what is the percentage for the metal? Then that's going to be 100% subtract 42.1%. That makes sense, right? Because we know the percent composition for those two elements should be 100, because in this compound they only have those two compounds add together. Make sense, right? Yeah. So this is the percent composition that we talk about. Okay. Well, this one is pretty straightforward, and also we already do that in our experiment. So today we're continue to do the percent composition lab. So we will emphasize your memory on this topic. The next part we are going to talk about is sometimes we can base on the percent composition to figure out the empirical formula. Okay. The next part we're going to try to figure out how to convert the percent composition to the empirical formula. And also how to convert the empirical formula to the molecular formula. Okay, so before we're doing this, we first need to figure out what exactly is the empirical formula. So what exactly is the molecular formula? Empirical formula, what is the difference between empirical formula and what is the difference between molecular formula? Okay, so empirical formula. So let's see some of the examples. Then you probably will know. Let's see. First one is a molecular formula. Then is an empirical formula. So some of the we know sugar, C6H12O6. So this is the sugar for a formula. Okay, C6H12O6. But when we write the empirical formula, then that's just a CH2O. Okay, so that's the empirical formula. If we have a CO2 for a molecular formula, the empirical formula will be still CO2. Molecular formula, if we have P, yeah, that's not using this. Okay, so H2O2, this is the peroxide, hydrogen peroxide. Okay, and then the empirical formula will be just a HO. Okay, so let's see some others. For the empirical formula, N2O4, the empirical formula will be just a NO2. All right, so I'm giving you the 4 examples. Can you tell what is the difference, or can you, based on those 4 examples, make a conclusion about what is the empirical formula, what is the molecular formula? Okay, so this guy So obviously you're simplify the ratios of there, right? So for the empirical formula is simplify the ratio for the molecular formula, right? And hydrogen peroxide is doing the same thing. We're simplifying the ratios. The N2O4 also simplified. Okay, then the point is why the CO2 still have the same CO2 as the empirical formula. Because it's already simplified. Okay, so this is a 1:2 ratio between carbon and oxygen. So this is also 1:2. 1:2 is not be simplified. Okay, yeah. So, but I do see some of the students they write CH4. They simplify it, become C2. Okay, so this is not right because they forgot this is 1. Okay, so 1 verse 4 is already simplified. You cannot make a 1 verse 2. Those are two different ratios. All right, so now you know the difference between molecular formula and empirical formula. Okay, so we can base on the mass percent of the compound to figure out the empirical formula, not molecular formula. Okay, we can figure out the empirical formula. Okay. Another concept I want you to understand is, okay, for example, CH2O, they are having the ratio. This, okay, CH2O, you can think about this means and the C6H12O6, they are going to have the same ratio between the atoms, right? So carbon versus hydrogen versus oxygen, the ratio will be the same, just 1 versus 2 versus 1. Yeah, doesn't matter is this one or this one. They are going to have the same ratios. And the ratio over here could be 1 atom, 1 carbon atom versus 2 carbon atoms and versus 1 oxygen atoms. The ratio could be the ratio between atoms. Okay, but I'm telling you now, the ratio could also be in moles of those because the moles is just a number of the atoms, right? So this ratio could also be 1 mole of the carbon versus 1 mole of the hydrogen, or 2 moles of hydrogen and 1 mole of the oxygen. So the ratio over here could be the atom ratio and it could also be the mole ratio. So that is why we can just base on the mass percent to figure out the, we just need to base on the mass percent to figure out the mole ratio. Okay, as long as we figure out the mole ratio, we generally can figure out the empirical formula because the ratio here is both the atom ratio and mole ratio. So as long as we figure out the mole ratio of the elements, then we should be able to figure out the empirical formula. Okay, so I'm going to show you one of the example. So let's look at the question number 2 in the page 5. Question number 2 in the page 5. So now we have some of the oxides, chromium oxide, and we don't know what is the ratio between the chromium and Y. So we don't know what is X versus Y. So we try to figure out the ratio between X and Y of there. So now what we have, we know the chromium is 68.4 another gram percent in this compound. And we know the oxygen, that's going to be the rest of the part, which is 31.6%. Okay, we know the percent composition for each of the elements, and we try to figure out the ratio between X and Y. Okay, so the best way to solve this problem is you need to figure out the mass for each of the compounds. Okay, to figure out the mass, actually the best or the easiest way is just you assume we have a 100 gram of the chromium oxide. We have 100 gram of this compound. So based on the percent composition, 100 gram multiply this will be just the mass of the chromium. And 100 gram multiply 31.6, that's going to be just the mass of the oxygen. Okay, yeah, because this is the mass percent. Remember, how do we do this? The mass percent is the mass of chromium divided by the mass of the compound. So this 1 times 100, you just got the mass of that, right? So the easiest way to convert those to the mass, you just assume we have 100 gram of those compounds. So 68.4%, that means we have a 68.4 gram of the chromium. So this is first step. We got the mass of the chromium. And we are having 31.6 gram of the oxygen. Okay, so those are the first step. Once you got the mass, and then we need to figure out how many moles of each of the chromium, because you see, we try to figure out the mole ratio between the elements. So you need to figure out the mole for each of the elements. So we need to get the mole of the chromium. Well, how do we get the moles of chromium? What's the equation? Mass over molar mass. Okay, mass over molar mass. So mass of the chromium divided by molar mass of the chromium. Then you will get it. So mass of chromium where you have 68.4 gram divided by molar mass. Again, here is you divided by molar mass of chromium. It's not a molar mass of chromium oxide. Okay, because we try to, this is a mass of chromium. So you need to use the molar mass of chromium, which is 51.9961. 51.9961. And this is in gram per mole. Okay, so now you got this. Let's figure out 68.4 divided by 51.9961. And we got this. And to be honest, when you do the empirical formula questions, I recommend you keep 4 decimals for this question. Then you will have a better calculation or ratios. Okay, if you keep the number short, then sometimes you will get a weird number. Okay, so keep 4 decimals. 1.3155. And this is mole of the chromium. And doing the same thing to figure out mole of the oxygen. So that should be mass of the oxygen over molar mass of the oxygen, which is 31.6 gram oxygen divided by 15.9994 gram per mole of the oxygen. 31.6 divided by 15.9. And then you keep 4 decimals, 1.99751. And this is mole of the oxygen. Okay, so now you got the 2 ratios. So now again, we try to figure out the mole ratio between the mole of the chromium versus mole of the oxygen. So this is a mole ratio we're going to looking for, which is 1.3155 moles versus 1.9751 moles. Okay, so we got those 2 mole ratios. And then what we're gonna do? We're going to make those as a whole number. Well, a lot of people make a mistake is because they say, oh, make a whole number. So we can just round it. This one rounded to 1, this one round to 2, and we got a whole number. This is not what we do, okay? If you want to make a whole number for this one, you cannot round like this, okay? This is not a way to round those numbers, okay? So this is a technique, a math technique to round the numbers to a ratio. For example, okay, if we have two numbers, 0.5 versus 1 versus 0.25. So we have those three numbers. We try to make a whole number. What we do? We're not going to round this to 1. We round this to 0, right? We're not going to do this. How do we do this? We just need to look at those three numbers and look at which one is the smallest number. And then we make every number divided by the smallest number. Then we will have a whole number. Okay, usually this is what we do. So smallest number is 0.25. So all the three numbers is going to divide by the smallest number, which is 0.5 divided by 0.25, 1 divided by 0.25, and 0.25 divided by 0.25. So now what we have? We're going to have 0.5 divided by 0.25, which is 2. 1 divided by 0.25, you got 4. And the 0.25 divided by 0.525, you got 1. So the whole ratio between those three numbers is 2 versus 4 versus 1. You see, we're not going to round this number. Instead, we look at those three numbers, which one is the smallest number, and then we make a ratio. Okay, yeah, same thing over here, same thing out here. We just look at it. Okay, which one is the smallest number? Well, obviously, chromium moles is smallest number. So we divide by smallest number for this. Okay, so every time you're going to divide by the smallest mole number for it. So usually I'm doing this. You got those two numbers and then find the smallest mole number. Find the smallest mole number, and then you use the number divided by it. So 1.3155 divided by 1.3155. This one also divided by 1.3155. And then you will got, so this number, that's going to be 1. And your versus this number. 1.9751 divided by 1.3155, and you got 1.501. So this one is 1.5. Okay, yeah. Again, this is 1.5. It's still not a whole number. Then what we got? So for some of the cases, if you have some number like a 0.5, you don't round those numbers. You're still going to make those a whole number. Usually 1 versus 1.5. Then what do? The ratio generally is just a 2 versus 3, because this guy times 2, then you got a whole number. Okay, so this is just so this ratio is just 2 versus 3. Okay, just 2 versus 3. Any questions? Carter, I have a question. Okay, yeah. So this is how we do. Okay, yeah. So in the future, if you see when you figure out the ratios, you got 1 versus something 0.3. For example, you got a 1 versus 2.5. Then don't round the 0.5. The number should be 2 versus 5. That makes sense, right? If you have a 1 versus 3.5, then that's going to be just a 2 versus 7. Make sense, right? Okay, yeah. So this is one of the situation. And the other situation is just if you have a 1 versus 1.25, you're still not going to round, because 0.25 you times 4 will be a whole number. So this one generally is just a 4 versus 5, because you times 4 on this ratio, it's just a whole number. Okay, so only to these two situations, say 0.5, 0.25. If you meet 0.5, then times 2. If you have a 0.25, it times 4. Okay, yeah. I know you need to do the practice over here. So go ahead to work on the question number 4. Okay, go ahead to work on the question number 4. Based on the mass of each of the compounds, and then to figure out the ratio. Okay, yeah, so now I'm going to put this pathway. So just doing the pathway. Since this one, the question number 4, you already have the mass. You don't have to convert that to the mass. Okay, you just have the mass. Once you have a mass, you just need to figure out the mole of each of the elements. Okay, then make a ratio to figure out the empirical formula. Oh, sorry. Yeah, actually we haven't done this. The ratio we got is 2/3, but this is not an empirical formula. Empirical formula is the formula you're gonna write out, which means the empirical formula. So we're looking for chromium X over Y, right? So the ratio X versus Y is 2/3. So the empirical formula for this one is a Cr2O3. This is called the empirical formula. The ratio is not called the empirical formula. This is called the empirical formula. Okay, yeah. So go ahead to work on the question number 4. Okay, so let's review this parts. And this one is talking about, we have the math for three different elements. We have 38.43 gram of the lead. And we have 17.83 gram of the carbon. And we also has 3.74 gram of the hydrogen. So now we have those three. Again, you're gonna figure out the mole of each of this. Mole of the lead is mass over molar mass, 38.43 gram, divided by the molar mass of the lead, which is 207.2. Carbon 17.83 gram divided by molar mass of this, which is 12.0108. And this one, mole of the hydrogen, is just 3.74 gram divided by 1.008 gram per mole. Okay, so now we set up those, we just need to figure out the numbers. .43 divided by 207.2. So 0.18455. $17.83 divided by 12.0108. 1.4845. Okay. Yeah, 1.4845. Last one, 3.74 divided by 1. 3.7103. Okay, so now we got this, which means the ratio between each of those elements will be lead versus carbon versus hydrogen will be just a 0.1855 versus 1.4845 versus 3.7103. And then again, then you look at which one is the smallest mole number, and then we're going to divide by that. So obviously this one is smallest mole number, so we just divide by 0.1855, and this one divided by 0.1855. This one also divided by 0.1855. Okay, and then let's see what's the final ratio. And obviously this one is 1, the verse, the next one, 1.4845 divided by 0.1855. Got 8.00, so absolutely it is 8. Okay, so that's just 8. And verse 3.7103 divided by 0.1855. We got 20. Okay, we got 20. So that's going to be 20, which means the ratio between those guys is 1 versus 8 versus 20. So the formula, empirical formula, will be just 1 of the lead, 8 of carbon, and 20 of the hydrogen. So that's going to be the empirical formula. That makes sense, right? Pretty straightforward, right? As long as you got the mole ratio for each of the moles or for each of the elements, then you should be able to, based on those moles, to figure out the mole ratio between each of the elements. Then you figure out what is the empirical formula. Make sense, right? All right. All right. So before the end of semester, I'm going to do a magic. So now what we have is a piece of paper, okay? Yeah, we have a piece of paper. And then we try to just cut those two together, then we will see. And this is a magic for called the intermolecular force. This is the topic we're going to talk about in the very end of the semester, but I would like to show you this, okay? Intermolecular force, that means we have the force in between different molecules, then they are going to have the attraction, which means they are going to attach to each other. Okay, yeah, let's see. So we have two of the papers, right? So we're going to just cut those the bottom parts. Okay, then let's see what happens. Let's see. Hey, if you didn't see that, let's do one more time, okay? One more time. Still working? Yeah, still working. Let's see, how about the diagonal way? Still working. That's the magic trick. And this is intermolecular force. Hopefully, it will attract your attention on this part. Okay, yeah. Chemistry is interesting. All right, so the next part we're going to, you want to know how? You can show the trick to the other people. Okay, so I'm going to assign some of the homework for you. Okay. Okay, so let's turn to the page 2. Find out the molar mass. So 1 A, B, C. Okay, find out the molar mass of the ABC. The former mass is just a molar mass. Okay, try to figure out what is the molar mass of those. Okay, and then page 3. Seven, 8, 9. I know they already give you the answer. Okay, at the end of in the parentheses, in the bold letters. I mean, those are the answers. But I want you to show the work. Okay, which means I hope you know how to do this work. Well, I know a lot of some, not a lot, but I do see some of the students, they set up the equation and just write the answer over there. Okay, yeah, they even don't do the calculation because I obviously see they set up the wrong set up the calculation, but they still got the correct answer. Okay, yeah, which means they just set up the equation, but they didn't answer the calculate. This answer is helping you to check your result. Okay, yeah, so I hope you're still doing work, then you know how to do the work. And page 4, 6, 7, 8. No, that's maybe too much. And I think I already talked about one. So, five and 6. Okay. Page 5. Question 5. And question 7. Okay, so that is the homework we're going to do. And on Tuesday, we're also going to have a quiz. And generally, the quiz is the same thing like your homework. Okay, find the molar mass of certain compounds and try to figure out what is the how to convert the mole to the mass or mass to the mole. Okay, and then we have a one empirical formula question. Okay, yeah, all right. So let's move to the lab, and we're going to work on the part 2 of the 2.0.